What happened before the Big Bang? Well, that's one hell of a question. For decades, the greatest minds in science and cosmology have battled to give a conclusive theory that accounts for the time before the Big Bang took place. But that hasn't happened, at least not yet. According to the Big Bang, the singularity just came up, blew up, then this happened and that happened, giving us our changing, expanding, and perfect universe where everything is just right. That raises a lot of question marks. How can something come from nothing? What is the origin of the singularity, and what caused the singularity to explode? Over the years, scientists have brought up theories and ideas which could potentially solve all these questions. Well, let's find out. All right, let's do a little bit of history. In earlier ages, ancient Greek philosophers entertained the idea of an eternal universe existing infinitely without a beginning or an end. They suggested a cyclical view of time, where the universe undergoes repetitive cycles of creation and destruction. In these cycles, different phases take place. In the first phase, the phase of creation. This involves the birth or formation of matter, energy, space, and time. It could include the formation of galaxies, stars, planets, and other cosmic structures. For the second phase, the cycle's existence, various ages or epochs unfold, each characterized by different stages of development. In these stages, events like the evolution of life, rise and fall of civilizations, the development of celestial bodies, and the unfolding of cosmic events will take place. The third phase, as the cycle progresses, it reaches a stage of culmination or transformation. This phase might involve significant events or changes, marking the cycle's completion. It could encompass cosmic events, transitions, or transformative processes leading to change or transition. Following the culmination phase, the cycle moves into a phase of dissolution or destruction. This phase might involve the decay, destruction, or dissolution of cosmic structures, the cessation of existence, or a return to a more fundamental state. After this, the cycle just restarts over and over again, infinitely. Interesting fact, this idea wasn't just a Greek thing. Certain schools of Hindu and Buddhist philosophy and cosmology also entertained the notion of an eternal universe, also involving similar cosmic cycles which they called kalpas, or yugas. But if you were to fast forward to the mid-20th century, an almost similar theory was proposed. In the 1940s, astronomers Hermann Bondi, Thomas Gold, and Fred Hoyle formulated the steady-state theory, which also suggested an eternal but unchanging universe. This theory proposed that the universe had no beginning and no end, but it also posited that new matter was continuously created to maintain a constant density as the universe expanded. But contrary to the eternal universe theory, the steady-state theory doesn't involve distinct cycles of creation and destruction, but instead proposes a perpetual, unaltered state for the universe. This theory remained the most prominent explanation for the universe's origin, up until significant evidence supporting the Big Bang emerged, completely shattering all grounds of the steady-state theory. Well, on the other side of the argument existed the Big Bang theory, which proposed the concept of a universe expanding from an infinitely tiny, initial dense state. This theory was first proposed by a priest of the Roman Catholic named Georges Lemaitre in 1927. Lemaitre formulated his theory based on Einstein's theory of general relativity. Although he initially believed the universe to be static and unchanging, his equations later revealed that the universe could not remain static but must either expand or contract. At the early stages of his work, Einstein introduced a cosmological constant, later known as the cosmological constant, to maintain a static universe within his equations, which he later referred to as his biggest blunder, once evidence for cosmic expansion emerged. This also suggested that the universe was once much smaller and denser, and has been expanding ever since. Although Lemaitre was first to propose the theory of an expanding universe, the British astronomer Fred Hoyle coined the phrase, the Big Bang. He used it somewhat dismissively in a radio broadcast in 1949 while discussing Lemaitre's theory. Originally, we mentioned Fred Hoyle was among the founders of the steady-state theory, so then what happened to cause a shift in interest to the Big Bang theory? Well, we aren't quite certain. But in 1964, something happened that caused a shift in the entirety of the scientific community in favor of the Big Bang theory. In 1964, Arno Penzias and Robert Wilson were conducting experiments at the Bell Telephone Laboratories in Holmdel, New Jersey. They were using a large radio antenna designed for satellite communication. Penzias and Wilson noticed an unusual and persistent background noise in their experiments. It was a faint but steady signal that seemed to come from all directions in the sky, regardless of where they pointed the antenna. They initially attributed the signal to various potential sources of interference, including pigeon droppings and nearby radio transmitters. They meticulously worked to eliminate any possible sources of contamination or interference. Frustrated by their inability to eliminate the noise, they sought advice from several prominent physicists, including Robert Dicke, James Peebles, and David Wilkinson from Princeton University. These theorists were actively working on predictions related to the cosmic microwave background radiation. The Princeton team quickly recognized that the signal detected by Penzias and Wilson was consistent with what they expected from the predicted CMB. The faint radiation Penzias and Wilson were observing was a remnant from the early universe, a snapshot of the cosmos when it was just 380,000 years old. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for their discovery. Their findings confirmed the existence of the CMB and provided strong empirical support for the Big Bang theory. But there's just one little issue. How would it address the rapid expansion found in the universe? In 1929, American astronomer Edwin Hubble published his seminal paper presenting observational evidence that galaxies were receding from one another, demonstrating the expansion of the universe. He arrived at this conclusion by studying the redshifts of galaxies and their distances, which led to the formulation of Hubble's law. This discovery laid the foundation for the concept of an expanding universe. This brings us to the concept of universal expansion. It suggests that galaxies, stars, and even the fabric of space itself are stretching and moving apart. Imagine floating in the vastness of space, surrounded by a celestial symphony of twinkling stars and swirling galaxies. But wait, something incredible is happening. The universe itself is stretching, growing, and expanding like an intergalactic bubble. Scientists and cosmologists have plundered the science behind such an incredible and mind-boggling expansion. Well, I might just have the answer to all their questions. I expect we all have an idea about gravity, but how much do you know about it? Sure, we all know it as the force that pulls and keeps everything in the universe in place, but let me shock you a bit. Did you know that the force of gravity goes both ways? The force of gravity can have two manifestations. The usual form, of which we know is attractive form we experience on Earth. You drop something toward the Earth and it moves downward because the Earth and the object pull on each other. That's the ordinary gravity that we experience every day of our lives. But Einstein's equations actually allow gravity to also be repulsive. It can push outward, as opposed to just pulling inward, and this is something that we have never experienced, because the gravity created by a rocky object like the Earth is always the attractive variety. The gravity created by the Sun is. Oh wait. Compact objects are always the attractive variety. But Einstein's maths shows that you don't have a rocky object that's isolated in space, but rather energy, that it's uniformly spread through a region of space. That kind of entity yields repulsive gravity. In the very early universe, if it was filled with a uniform bath of this energy, we call it the inflaton field. An inflaton field? We'll come back to that in a bit. But the name doesn't really matter yet, but if space as we know it was filled with that energy, it would have been subject to repulsive gravity. What does repulsive gravity does? Pushes everything apart, causing everything to rush outward. So the bang of the Big Bang may have been a spark of repulsive gravity operating with a tiny region of space that pushed everything apart. Universal expansion involves the stretching of space itself. To truly grasp the universe's earliest moments and its subsequent evolution, cosmologists devised a cosmic chronology, a captivating tale that unraveled the history and future of the cosmos within the framework of Big Bang cosmology. Let's dive into the first picosecond of cosmic time, a mere blink lasting 1,000,000,000,000th of a second. Within this infinitesimal span, we encountered the Planck epoch, a time so extraordinary that our established laws of physics may not have applied. It was like entering a realm where the rules of the game were being rewritten, challenging our understanding of the universe's very fabric. As cosmic time marched on, the stage was set for the appearance and progression of the four fundamental forces. First, gravity took center stage, followed by the emergence of the electromagnetic, weak and strong interactions. It was a cosmic ballet of forces unfolding in the vast expanse of space itself. Amidst this grand cosmic spectacle, the universe underwent an incredible transformation called the cosmic inflation. Picture the universe rapidly expanding, cooling down, and evolving. In this process, tiny ripples in the universe at this stage are believed to be the basis of large-scale structures that formed much later. The universe almost certainly did not explode from a singular point. We covered that misconception recently. These days, the best accepted description of the time before the Big Bang is given by inflation theory. The idea is that the energy trapped in the inflaton field causes exponential expansion of space. This was the bang in the Big Bang. But we have to note that if we accept that inflation happened at all, then it's going to be hard to escape the conclusion that it never actually stopped and is causing the rapid expansion found in the universe. And in fact, our universe is but one bubble among countless others in an eternally inflating greater universe. Cosmic inflation was driven by the inflaton field, which had the bizarre property of containing a ton of energy even in the absence of particles. It had a non-zero vacuum energy. Before we make any real predictions about the behavior of an inflating universe, we probably should know more about the field that drives it. To start with, you need a particular type of field to cause inflation, something called a scalar field. This is actually the simplest type of quantum field because it's described by a single number, a scalar everywhere in space. Other fields like the particle field or the electromagnetic field are described by multiple components and vectors instead of single numbers. We know that scalar fields exist, or at least one does. That's the Higgs field, which gives elementary particles their mass. The inflaton field would be another such scalar field. Or it might even be the Higgs field. Physicists are still arguing over that one. You might want to know that quantum fields can hold energy without actually having particles. They do this through a process called self-interaction. Just think of a field with a high field strength as being full of virtual particles. These are ephemeral vibrations in the field that are constantly tugging at the field as the field tugs at them. This self-interaction gives the field some potential energy. It's potential energy because the field would much rather reconfigure itself into a lower energy state, in which case that stored energy would be converted into another form, for example, into real particles. Although scalar fields are the simplest, they can exhibit complicated relationships between this potential energy and the field strength. In the case of old inflation, proposed by Alan Guth in 1979, Guth put forth a mind-blowing idea that would forever change our understanding of the early universe. Picture this. In the first moments after the Big Bang, the universe experienced a mind-boggling exponential expansion, far surpassing anything we could have imagined. Guth called this phenomenon inflation, a cosmic growth spurt that occurred within a tiny fraction of a second. Guth's ingenious proposal aimed to resolve some puzzling aspects of the early universe. It explained how the universe became so uniform on a large scale, why it appears flat, and why there aren't an overwhelming number of magnetic monopolas, exotic, hypothetical particles. Inflation was the cosmic magic trick that offered elegant solutions to these cosmological conundrums. But how did Guth's inflation work? Well, according to his theory, the universe underwent a brief period of extreme expansion driven by a peculiar energy field. This field, known as the inflaton field, possessed a unique property. It contained a tremendous amount of energy, even without the presence of particles. During inflation, the inflaton field caused space itself to rapidly stretch, like cosmic taffy being pulled apart. It smoothed out irregularities, making the universe remarkably homogeneous and flat on large scales. It was like ironing out cosmic wrinkles and giving the universe a sleek, uniform appearance. But, as quickly as it began, inflation came to an end. The inflaton field released its stored energy, igniting a period of reheating and setting the stage for the subsequent hot and dense state of the early universe. This phase would eventually lead to the formation of particles, atoms, and the cosmic structures we observe today. Guth's groundbreaking idea of inflation sparked a revolution in cosmology, providing an elegant framework to explain various puzzling aspects of the universe's structure and evolution. It has since become a cornerstone of modern cosmological theories, shaping our understanding of the cosmos on both the largest and smallest scales. But, in Guth's idea, there's a local minimum in potential energy that allows the inflaton field to get stuck in a false vacuum state. When that state decays, potential energy is released as real particles, ending inflation and reheating the universe in an expanding bubble. The random nature of this version of inflaton decay means that many such bubbles should form, multiple universes exist. But we also saw that there were problems with this approach. Old inflation predicts empty firewall bubbles that look nothing like the early phase of our universe. But a more promising idea is something called slow-roll inflation. This was proposed by Andre Linde, Andreas Albrecht, and Paul Steinhardt in 1982, just a few years after Guth's proposal. The idea of slow-roll inflation is that the inflaton field isn't stuck at a local minimum in the potential, but rather it's on a very weakly sloping plateau leading towards a deeper valley. In that case, the field strength would very slowly roll down that slope. As it did, the energy would drop very, very slowly. That would still give us our near-constant energy density needed to power inflation, and then, as the roll sped up towards the valley, inflation would end. But it wouldn't end as a random process. It wouldn't require quantum tunneling to get started. Instead, the entire region of the inflating universe would approach this minimum at the same time. Inflation would shut down smoothly, and the universe would be reheated everywhere all at once. This gives us the expanding, hot, dense universe that we know and love in our Big Bang model. As speculative as inflation is, it does make some predictions. One of such is that quantum fields fluctuate due to the intrinsic randomness of the quantum world. So as the inflaton field rolls down the potential energy hill, the field strength should fluctuate slightly. That means some regions of the universe would finish inflation a little ahead of others, and that will lead to very small density and temperature fluctuations in the matter produced after inflation. And we see those fluctuations in the cosmic microwave background. These same fluctuations collapsed under their own gravity to become the first galaxies. In fact, this is perhaps the best evidence we have that inflation is plausible. It can predict the pattern of temperature fluctuations in the CMB. But if slow-roll inflation stops everywhere at once, how does it last forever? And how does it give us multiple universes? Seeding all of the structure in our universe is probably the least impressive thing those quantum fluctuations did. They also give eternal inflation and multiple universes. In slow-roll inflation, exponential expansion should grind to a halt over large regions as the inflaton field decays. Small fluctuations in the inflaton field would lead to slight differences in when the inflation ends from one point to the next. So now we've established the possibility of a multiverse. The fact that a primordial event called cosmic inflation, which took place just after the Big Bang, could be reason for the rapid expansion and redshift found in the universe, and that what happened before the Big Bang was an eternal cycle of inflation which continually creates new pocket or bubble universes within a larger overarching multiverse. Alright, this is where I will end this video. Like, subscribe, share your thoughts down in the comments, and I'll see you in my next video.